This video marks the first in our official journey through biochemistry. In this unit, and starting with this video, I hope to help you understand that in biology class, knowing a few rules and seeing a few patterns is the key to making connections between biology and chemistry. This is video 5.1 on chemical bonds. Video 5.1 will cover these three objectives. Pause for a closer look. Put simply, chemistry is the study of matter and the changes that matter undergoes. But what is matter exactly? By definition, matter is anything with mass and volume, and all matter is made up of simple building blocks called atoms. For biology, we also need to remember the subatomic particles that make up atoms. The atom's nucleus is made up of positively charged protons and neutrally charged neutrons, along with the negatively charged electrons that move around the nucleus in orbitals or clouds. A bunch of atoms of the same type is called an element, and living things mostly depend on just 25 of the over 100 elements on the periodic table. The big six most abundant elements in living things can be remembered with the mnemonic SPONCH: sulfur, phosphorus, oxygen, nitrogen, carbon, and hydrogen. You knew it was coming. Our friend, the periodic table, that organizes elements into chemical groups or families. So the groups on the periodic table are organized based on how many valence electrons an atom has, 1 through 8. Now, remember, valence electrons are the electrons in just the outer shell, outer electron cloud of an atom. Valence electrons help determine the chemical properties or reactivity of an atom. One other thing to remember about valence electrons is the octet rule. The octet rule reminds us that atoms are most stable with a full outer shell of valence electrons. See how this oxygen atom over here looks pretty ordinary with 6 valence electrons in its outer shell? Doesn't this oxygen look much happier now that it has an octet of valence electrons? So think about an atom's life as kind of like a quest for happiness, to get this full outer shell of valence electrons. Now, what will atoms do to get that full outer shell? Well, atoms will react with other atoms in chemical reactions. Atoms can gain or lose electrons in reactions to satisfy the octet rule, forming ions and ionic bonds in the process. And atoms can also share valence electrons and end up forming covalent bonds. We can see bond formation in action by looking at the interaction between a sodium atom with 1 valence electron and a chlorine atom with 1, 2, 3, 4, 5, 6, 7 valence electrons. Now, this is a match made in heaven. You see, if sodium gives this valence electron to chlorine, then chlorine will have 8 valence electrons. Now, it seems sad that sodium will seemingly have 0 valence electrons, but getting rid of that 1 just exposes the full shell of 8 valence electrons underneath. So sodium's actually really happy too. Now, when giving up a negatively charged electron, the neutrally charged sodium atom becomes a positively charged sodium ion. And by gaining this negatively charged electron, the neutral chlorine atom becomes a negatively charged chloride ion. Besides the octet rule, another rule in chemistry is that opposite charges attract and like charges repel. And since these ions have opposite charges, positive and negative, they form an attractive force, and this attractive force is an ionic bond. Another way of satisfying the octet rule is by sharing valence electrons. Very small atoms like hydrogen can fill up their outer shell with only 2 valence electrons. Yep, those little atoms go by the duet rule instead of the octet rule. Anyway, neither hydrogen atom wants to completely give up its valence electrons, so they end up in kind of this tug of war where they're sharing, and each atom feels satisfied that its outer shell is full. Likewise, oxygen over here is on the hunt for 2 valence electrons to add to its 6 that's in the outer shell. And so oxygen shares 1 valence electron each with 2 different hydrogen atoms. And the result is the strong covalent bonds that bind hydrogen to oxygen in water, and neither atom in the covalent bond wants to let the electron go. Covalent bonds can actually get even stronger if the atoms in the covalent bond share more than one pair of electrons. There can be double covalent bonds, like in oxygen gas and carbon dioxide, double covalent there, and even triple covalent bonds, like in nitrogen gas right here. Living things use the bond strength of covalent bonds to their advantage. When living things need molecules to stay together, you can find strong covalent bonds linking those atoms and those molecules together. How strong are we talking here? Well, about 100 to 400 kilojoules of energy are needed to break a mole of covalent bonds. In comparison, only about 50 kilojoules of energy are needed to break 1 mole of ionic bonds. So in living things, covalent bonds are about, 2 to 8 times stronger than ionic bonds. Now, there are other weak bonds besides ionic bonds, like hydrogen bonds, hydrophobic and hydrophilic interactions, and van der Waals forces, and we'll get into those a bit later. Now, atoms share electrons in covalent bonds, but what if that sharing isn't equal? What if one atom gets a little bit and the other atom gets a whole lot? Well, that's just a special case of covalent bonds. There are a couple different classes of covalent bonds. A nonpolar covalent bond forms when valence electron sharing is relatively equal. But when valence electron sharing is unequal, we call that a polar covalent bond. And there are consequences to that we'll check out right now. Now, whether a bond is polar covalent or nonpolar covalent or ionic can be determined by looking at the electronegativity difference between the bonding atoms. Now, don't panic, I got you. Let me just explain what this means. Simply put, electronegativity is a measurement of how badly an atom wants electrons. Elements with higher electronegativity will attract electrons to them, and elements with a lower electronegativity are more likely to give those electrons away. The trend on the periodic table is that if you move up and to the right on the periodic table, elements will have a higher electronegativity. So fluorine atoms have the highest electronegativity. Now, this makes sense because these are the group 7 atoms, and that means they have 7 valence electrons. So think about how badly they want that one more valence electron just to get that octet. These guys over here are in group 1 of the periodic table, and it's like, yo, if I can just get rid of this at 1, then my next outer shell underneath will be full. All right, so let's use this to examine the most famous covalent bonds in biology, those bonds between the oxygen and the hydrogens of water. To evaluate this bond, we need to look at the electronegativities of oxygen and hydrogen. Oxygen has an electronegativity of 3.5, so let's write that over there, and hydrogen has an electronegativity of 2.1, so let's write that next to the hydrogens. And what we care about is the electronegativity difference. So 3.5 minus 2.1 gives us a difference of 1.4 on each of those bonds. Now, when we decode this on our chart, this tells us that the bonds between oxygen and hydrogen are polar covalent bonds. Well, let's think about what this means. So based on that chart, we see that water has polar covalent bonds. Now, the higher electronegativity of oxygen means that oxygen attracts the shared electrons more than hydrogen. In other words, electrons will be around the oxygen more than hydrogen. So to show that a little bit better, I want to redraw these bonds. I like having these arrows here better as a visual. So the arrows are showing us that the electrons are more attracted to oxygen in these polar covalent bonds. So still, why do we care about that so much? Well, what this means is that oxygen will have a partial negative charge because those negative electrons are hanging around the oxygen more often. Now, in biology, we use the Greek lowercase letter delta to show that the negative charge is a partial negative charge. On the flip side, since those negatively charged electrons are around hydrogen less frequently, hydrogen is said to have a partial positive charge, marked with the Greek lowercase delta positive here. So since water has opposite charges, positive and negative, on those opposite sides, this makes water a polar molecule. And it's huge to understand this, so I just want to be really clear. So since the water has positive charges on the hydrogen side and negative charges on the oxygen side, we call water a polar molecule. A molecule with a positive side and a negative side. A molecule with a positive pole and a negative pole, just like the North and the South Pole. That's where this polar comes from. But the reason that water is a polar molecule is because of the bonds between oxygen and hydrogen. And those bonds are polar covalent bonds. So even though these concepts are related, it's really important to understand the difference and not be intimidated by the difference. Because water is a polar molecule, water can do really cool things. And this is because of water's ability to form another type of bond called a hydrogen bond. A hydrogen bond is a weak interaction between the partial positive charge of one water molecule and the partial negative charge of a nearby water molecule or other atom with these partial positive and partial negative charges. So it's kind of like an ionic bond where we have a case of opposites attract, but hydrogen bonds are kind of like partially opposites partially attract, and the bond force is a little bit weaker. The last type of bonds I want to talk about are hydrophobic and hydrophilic interactions. And these aren't really technically chemical bonds, so interactions is a better word to describe them. The best way to think about these interactions is to think about how water and oil don't mix, like in salad dressing. And this is because water and any molecules that are polar and charged are called hydrophilic or water-loving, while oil or any molecules that are nonpolar and uncharged are hydrophobic or water-fearing. Now, because opposite charges attract, water and the other polar or charged molecules will have that force of opposites attract, and those hydrophilic molecules will interact with each other, leaving oil and the other hydrophobic molecules out of the cool kids club here to interact separately. The resulting interactions, hydrophilic interactions and hydrophobic interactions, are weak forces that we'll use a little bit later on to help us understand more complex biological structures. Now, one thing that I want you to remember is that these hydrogen bonds, hydrophobic interactions, hydrophilic interactions, and ionic bonds are all relatively weak compared to covalent bonds. So when biological systems only need molecules to stay together for a bit or very weakly, living things use these types of bonds. So that's it. That's our whirlwind tour of chemical bonding. I want you to remember that chemical bonding properties are largely determined by the number of valence electrons that an atom has. And atoms do chemical reactions and attract to each other to get an octet or 8 valence electrons, or to place a positive charge next to a negative charge and neutralize those charges. When atoms share valence electrons, this is called a covalent bond, and covalent bonds are strong. In contrast, the transfer of valence electrons creates a relatively weak ionic bond. And other weak types of chemical bonds are hydrogen bonds and hydrophobic or hydrophilic interactions.